Okay, students, today we are going to, like I said, I was going to record a video on the calculation of calculating electric fields and charge distributions, simply because I wanted to just provide um, or be able to make the best use of our time in class, going through various examples, and therefore having to potentially scan over or just really outline some of the integrals that I do when I do this very difficult direct integration method. I say very difficult, not really, because that's probably not accurate. It's not really all that difficult. It's just lengthy and cumbersome, and you have to be really careful with the integrals in order to calculate them correctly. But it's easy in the fact that it is extremely straightforward. You just simply use Coulomb's law, break up a charge distribution and assume that it's something similar or identical to a collection of point charges, and then just use Coulomb's law and integrate over the charge distribution. So it's extraordinarily simple from a conceptual point of view, but the calculations, as you will see, can become a little bit lengthy. And that's where Gauss's law, the method to calculate fields using Gauss's law, comes in. That's method B. Method A is the direct integration. Method B is the method that uses Gauss's law. That is a step up in terms of conceptual sophistication, might be a better way of saying it. But it makes the calculations far and away easier when you can use method B, the method that uses Gauss's law. You can't use it in all situations, as we will see. All right. So first, calculation of fields, electric fields of charge distributions using the direct integration method. So we're going to do a simple example of this. Learning this is best done by doing a simple example of a linear point charge. Now, I apologize, for some reason the imager on my scanner has these two lines that are malfunctioning, and so you'll see that on every page. I'll rescan this on a better scanner in the school and upload those to the notes on the Moodle site, and you won't have that. But it doesn't get too much in the way of the figures and the writing, so we'll go ahead and make the video now with this series of notes. Anyway, so we're going to be looking at this line charge here, and we will do so. This line charge will be infinite, meaning that you go up to infinity with this line and down to minus infinity with this line, and it's going to have a charge density of rho sub L, which that represents the amount of charge per delta L length along the line. All right, and so like I said, when I introduced the direct integration method as being conceptually simple, we are going to break up this line charge into small little delta L segments and treat each delta L segment that will have a dq of charge within each segment as a point charge. All right, and simply use Coulomb's law to figure out the field at any position r away from the line. Okay, so we set up the problem like this. We choose to calculate the electric field at some position r along the y-axis, and we define what theta is right here. The distance from the point charge to the position that we're interested in, that will be my r prime. And this point charge, it will produce a field, contribution to the field of an amount d sub e. So therefore, that contribution has both a magnitude and direction, and that's what we aim to calculate. So a few little geometric definitions and functions that are straightforward. R prime is equal to r squared, the square root of r squared plus z squared. Tangent of theta is opposite over adjacent. Our opposite is z, and our adjacent is r. And my cosine theta is adjacent over opposite over hypotenuse. And so that's what we have right here. Fine. All right. So now, so back up here. So now we're going to use symmetry. So to eliminate some of the work that we have to solve to find for the electric fields. All right. So we note that our line element is infinite in extent, meaning that it goes to positive z infinity and minus z infinity, or z is equal to minus infinity. So it goes up forever and down forever. Therefore, there's due to symmetry, there's not going to be any z position that's preferred over any other z position. All right. So it doesn't matter where we calculate this field along the z-axis. We could simply solve it at z is equal to 0, and it'll be the same here as here as here as here and here, and so forth. Therefore, we note that at the end of the day, or at the end of the calculation, our functional dependence, the dependence of E should only depend on R for its dependence on any distance term, and not on Z. All right, so that's one piece of information. Another piece of information are, can we say particular components of the electric field are 0 due to symmetry? And the answer is yes. We can say, we notice right away that any Z component of the electric field for the overall system, for the total system, namely the entire wire, the Z component must be 0. So you might say, well, no, that's not the case, because we just drew it right here where we have a non-zero EZ component, a Z component of E right here. And that would indeed be true. However, if we were to look at its partner charge segment, that is just as much on this side of the xy plane as this charge element was below the xy plane, it's going to have an E sub z that points down and having the same magnitude as this d E sub z. And therefore, those two charge elements, the Z component contributions to the electric fields will cancel out, whereas the Y component of those two, the Y components, plural, will add together. So, therefore, and that will be true for any charge element on any portion of the wire. You can find its corresponding member of it, namely the other part of the pair, such that the DEZs cancel out to be 0, and you're only left with a DEY. All right? And since the electric field is only radially outwards from the charge element, you will also, at this point along the y-axis, not have an x component of the electric field. So there's not going to be a DEX, and so there's certainly not going to be a EX when you integrate over the entire line. So it's only the E sub z's that you're concerned about. And so therefore, I'm sorry, it is only the E sub y that you're concerned about. And if you were to figure out what E sub y is in terms of E, or find out what DEY is, in terms of DE, it's going to be the cosine term. So it's going to be DEY, but you multiply by cosine to get the adjacent of the hypotenuse of the triangle defined by the hypotenuse DE. All right. And so this is now where you bring in Coulomb's law, because you know the D sub E, the contribution to the electric field produced by this dQ, It is simply Coulomb's law, dq over 4 pi epsilon naught r prime squared. But now we have to multiply it by the cosine term. And we know what dq is in terms of charge density rho, and my dl. What is my dl? We go back to here. My dl, we're going along the z-axis for this wire. So dl is equal to dz. So this is what we have for my dEy. All right? And this is what we want to integrate over, namely the z, going from minus infinity to infinity. All right? So this is what we have, and we put in what cosine is in terms of r and z, and so this is the integrand, where r is constant, rho l is constant, 4 pi epsilon naught is certainly constant. So the only thing that varies is z. Well, so that makes for a very easy integral to do. It's a simple trigonometric substitution. We can just simply go, and instead of integrating over z, we can integrate over theta. So we change our variable of integration from z and the limits, therefore, over to theta. And this is what we get when we do the substitution. So this is the integral that we get. Going from here to here, we just pull out constants and put them in front of the integral sign. And then we have secant squared over 1 plus tan squared theta to the power of 3/2. So 1 plus tangent squared theta, all to the power of 3/2. In the denominator, you used your identities, and you know that 1 plus tan squared is just secant squared. Taking secant squared to the 3/2 power gives you secant cubed on the denominator. Two of those secants cancel with the numerator's secant squared term. So you have 1 over secant, which is just cosine. The integral of cosine is sine, and you're taking it from this limit to this limit. And you put in those limits, and you get this is the result for e of y. So rho sub L over epsilon 2 pi r, all right? So, all right, so that's great, and that wasn't all that difficult to do. The integral turned out to be fairly simple once you switched it over to theta, and that's that. Okay. However, this is at a particular point along the y-axis, and in the xy plane. Can we generalize this result to any point in space? And the answer is yes, due to the symmetry of the charge configuration. So let's read this. We calculated the electric field at a particular point, but due to the symmetry of the structure, we can generalize this result for the equation for E at any point. Okay. So if we were to go back up a couple of pages. All right. So we calculated the electric field right here. All right, and found that it only depends on r, and that it only has a y component, meaning pointing straight away from the charge element. Okay, so what is, and so if we were to look at a point on the x-axis, a distance r away, how would we expect the direction of the field to point for that observation point, say like right here? Well, your intuition, and in this case, and in probably most cases, your intuition is correct that it would be pointing along the x-axis. All right. So we can continue with that analysis for different points, but we find that the direction is always radially away from the wire. All right. Radially for cylindrical coordinates. All right, instead of spherical. So it goes radially away from the z-axis. So that's the r hat vector. All right. So, and of the same magnitude. So it only depends on r. And so if this r would be the same, then the magnitude of the electric field would be the same thing. The rho sub L over 2 pi r epsilon naught, where r is the same as it was for this observation point. All right. So we can generalize this to this equation here, and we see that it only depends on r, and it's always in the r hat direction. Another thing to note that's very interesting is that it only depends on 1 over r, not 1 over r squared. 1 over r squared was what we got when we had just a point charge. And so we lost a factor of r in the denominator when we went from a point charge to an infinitely long line charge. So quite interesting. All right. So that's that for the infinite line of charge. So let's look at another example. The uniformly charged sphere. All right, this is a typical example that is generally done, but it's generally done in electromagnetics textbooks when we teach method B, the Gauss's law method of calculating electric fields. But I want to go through this example in a step-by-step fashion with method A as well, the direct integration method. And you can see that both methods produce the same result, but you see a couple of things, maybe two, at least two, maybe even more things. Let's list them off. First of all, you see that the direct integration method of solving for the field, here let's go down to where we actually draw it. Solving for the field at some observation point due to a spherical charge distribution, in this case a uniformed spherical charge distribution, you will find that it is quite difficult to do the integrals, but certainly doable. Another thing you will find, though, is conceptually straightforward, as I said with the line charge, using the direct integration method, because you're simply using Coulomb's law and breaking up this sphere into an array of point charges and applying Coulomb's law to each point charge. All right, so conceptually simple, but mathematically just a little bit cumbersome when you're using the direct integration method. And then when we apply to this problem method B, the Gaussian law method, we will see that we take a step up in sophistication of the concept, meaning that we use a more sophisticated, elegant method of calculating the fields, but the mathematics turns out to be much easier. All right, so let's go through this step by step. The power of the direct integration method is that it can be used to calculate the field for any charge configuration, So any weirdly shaped structure, we can always break it up into dVs, that each dV, or infinitesimal volume element, will have a dq, a certain amount of charge. And that we will consider it to be a point charge and apply Coulomb's law such that we can find the contribution to the total electric field due to this particular dq of charge, and therefore that contribution to the electric field is dE. And then we just are going to sum up all the charge elements in this dq. All right, so dE, as you know, each charge element will have a dq, and then we simply apply Coulomb's law and find the dE contribution, the E contribution for each one of these charge elements, right? Where the dq is equal to rho dV. All right. So the goal of this example is to calculate the electric field at any point in space that is produced by a uniformly charged sphere, and doing so using the direct integration method. All right, so this is how we're gonna. This is the problem we want to solve. So if we were to jump straight to the sphere, we would be breaking up each one of these things into dVs, each with a dq, and calculating the electric field. All right. Now, you would naturally say, well, shouldn't we be using spherical coordinates for this? since we have a sphere? And the general answer would be typically yes. Typically yes, but I want to wrap up into this example 3 examples. An example of calculating the field due to a ring of charge, and an example where we calculate the field due to produced by a disk of charge, and then finally the sphere. So, in fact, here, hold on. Let me load something up and see if it works. So this is what I want to do. Give me 1 second. All right, this should work. So this is what I want to do. Let me see if that's coming up. No, it's not. So I have to add another window. Add window capture. Yeah, I think this might do it. So this is what I... So I want to first do a ring of charge where I am going to be looking at an observation point right along the z-axis. And for that integration, I will break up that ring into small segments and integrate around the ring such that I can find the entire field at this observation point due to the ring. All right. And then what I'm going to do, once I know the field produced by one ring, I am going to express that field according to the distance above the ring of my observation point, and then I'm going to find the contributions due to all the rings that fill up this outer ring. So I'm going to do a second integral, and then I'm therefore going to have a disk. So my result of the ring naturally will allow me to get quite naturally the field due to a disk. And then once I'm done with that, I am going to stack up these disks. So let me remove this. Remove. Yes. And it didn't do it. Okay. So I'm going to add a second window capture. We get 2. And once I have the disk, I am going to stack up all the disks of different radii so that I can find now the field at an observation point due to the stack of disks. All right, excellent. And so that is what we're going to be doing in this calculation. Let's go ahead and get my notes back up. I guess that is what I... this. All right. So that's what I'm going to be doing in this calculation. All right, so let's remove the MATLAB code. Just have that and that. There. Okay, so that's our plan of attack. We will break up this problem into 3 steps: the calculation of the field produced by a ring of charge, and use those results to find the electric field produced by a disk of charge, and use those results to find the electric field due to a sphere of charge. The calculation of the 3 structures occurs naturally within the overall calculation if we use cylindrical coordinates. So this is how we're going to set up the first part of the problem. Having the disk of the ring of charge right here, and we're going to find the electric field at a z position h, where the ring itself is at a position z, and having a radius of r tilde. And therefore the distance between that charge element in the ring to our observation point is r vector prime, r prime vector, and so forth. So the general equation for this, the calculation of the field due to the entire sphere, is given by this integral in cylindrical coordinates. So in cylindrical coordinates, we have the d phi, we have the r tilde, the d phi, the dr tilde, and the dz. And we're going to be doing our phi integral first over 0 to 2 pi. Then we're going to be doing, and that will give me the ring, the field due to a ring, and then we're going to fill up the ring going from r is equal to 0 to r tilde going from 0 to r tilde going to r. So our second integral is going to be over the r tilde variable, and then finally we're going to be stacking the disk, therefore doing an integral over z, going from minus r to r. Meaning going from minus r, which is right here, to positive r. So the total radius of our sphere is r. All right, so that's the integral we're going to do. The first integral over phi will give us the ring of charge. The second over r tilde will give us a disk of charge, and the third over the sphere over z will give us the sphere of charge. All right, so let's break up and zoom in to the ring of charge. We have two nice figures that we can be working with here. So we're going to break up our ring into dl, dr, dz infinitesimal volume elements, each with a dq. And this is our dv right here. It has a dl of r tilde d phi. So the dl is equal to r tilde d phi, and then we have a dz and the dr. And therefore, the infinitesimal amount of charge in that volume element is rho sub b, the volume charge density, all right, times the volume. We have a width of dr, a height of dz, and a length of dl, which is just r d phi. This integral over the variable phi is very easy to do because you don't have any phi in here. So it's simply 2 pi times the integrand. R tilde is constant. So, and so what we're doing here, so the first things first is we want to find the charge in the entirety of the ring. So let me take a step back. So all this is doing is integrating over the entire ring's volume to find the total charge. All right, we'd like to have that for a later calculation that we do. All right, so, and it's extraordinarily easy. So we're finding the total charge in the ring is simply rho v dv, but we have a constant dr, we have a constant dz, we have a constant r tilde, and so we find that the charge in the ring is simply this right here. All right, so we tuck that away. We're going to use that later on. Now we do this integral, the integral to find dE. Okay, but do we actually need dE, or like in the line charge, do some field components cancel out due to the symmetry of the structure? The answer is yes. Both dEy and dEx cancel out, leaving us only with dEz that we're concerned about. And dEz is the cosine component. The cosine component. So we put in another cosine I mean, a cosine here, and then we have just Coulomb's law with the dq right here, and the 4 pi epsilon naught in the denominator, and the r prime squared going from our dq charge element to our observation point. The cosine term, when we put that in terms of z, it gives us some h minus e on the numerator, and another r tilde squared plus h minus e squared to the 1/2 power on the denominator, so we have a 3/2 down here. My h, my z, my r tilde is all constant. We can take it out to the integral, and we simply have this very simple integral to do, where we pick up a factor of 2 pi, and this is then the result. And we leave it like this with the 2 pi up there. So we don't cancel that out, because we recognize from the previous page that's what's in the brackets isn't just the Q of the ring. And so therefore this is what we have, Q of the ring. And that is my Z component of the electric field, which we said is the entire electric field at that observation point. So, and that's only true along the axis, the z-axis. If you go outside, beside the z-axis, you will have x's and y components in general. But along the z-axis, you only have the z component. So, now an interesting thing about this, what happens when our observation point gets to be very, very large? Remember, h is my observation point. My ring is centered about z is equal to z. And so we're going to let h become very large. Well, if h becomes very large, then we can neglect the r squared, and then we have h sub z to the 3/2, so square root of the squared, and then we have h minus z cubed. One of those will cancel with the h minus z in the numerator, and therefore we have q over 4 pi epsilon naught h minus z squared, where we let d be equal to h minus z. So we have a d squared, which is essentially the distance between the ring and the observation point. And what we see is that this field expressed by this equation is identical to that produced by a point charge at z is equal to d. All right, so both a point charge and a ring of charge look to be the same if they both have a q of charge. They both look to be the same if you go far enough away from the ring. And so you kind of lose the details of the charge distribution when your observation point is far from the ring. So that's quite interesting. Okay, so we have the ring of charge. Now let's use that result to find the field due to a disk of charge. So we now let us do the next integral over the radius such that the ring of charge becomes a disk of charge. Okay, so first let us calculate the total charge of each disk. So again, we're going to do one simple calculation that it will be nice to have this result that we'll bring into play later in the calculation. And that's find the total charge of the disk. Well, for that, we're just going to simply be adding up the charges of each ring that make up the disk, which in actuality is just simply the integral of rho v dz 2 pi r tilde dr tilde. All right, where we're taking r tilde from 0 to r. All right, while keeping dz as a constant, so that comes out. Of course, rho v is as well. So we do that integral, we get something very simple and very intuitive as well. That we get a q disk is equal to rho v, the charge density, times the volume of each disk, which is the area of the disk multiplied by the thickness of the disk. All right, so that makes sense. So that's our q of the disk. Okay, so now let's go ahead and do the integral of of this. So we have the DEZ for each disk, and we integrate now over that from 0 to R, getting the total electric field E sub Z. Okay, a lot of things are constant. My rho V, my dz, my h minus z's, my 2, my epsilon naughts, my r squared plus h minus z squared, those are all constant. The only thing that's not constant is my r tilde there, and so we have to leave those two terms in, and this is the integral that we're left with. Okay, that's not so bad. We do a substitution where we let u be equal to r squared, r tilde squared plus h minus z squared, and therefore we find du, and we look at how we need to replace our limits. We do this substitution, and we get this simple integral, the 1 over u to the 3/2 power, which is very easy to integrate. And we get to this result right there. So this is E sub z, right on the z-axis, and at an observation point H, due to a disk of charge oriented along the y-axis with its normal vector along the y-axis and at a position z. So this is what we get. So due to a disk of charge. Now, if we bring back in what we had for Q disk, we can express it in this way. So, all right, that's very interesting. Now, let's let the disk become very, very large so that it fills up all space. And then we have the H reasonably sized. So it looks from the observation point that you have an infinitely long sheet of charge. So that's what will happen if we let R, the radius of the disk, become very, very large. So what happens then in that case? Well, so first of all, R becomes very, very large, and so therefore we can neglect this portion of the denominator relative to this. So we have the square root of r squared, which is just r in the denominator. And so in fact, this entire term, and so then we have h minus z over r. All right, and whereas r is getting to be very, very large because we're letting our disk become very large. And so anything over r is going to be small relative to 1. All right, so it's going to be this term that dominates. So whereas this term goes closer and closer to 0 as my disk becomes very large. So we only keep the 1. All right, we also go back to a surface charge density, which is charge over unit area. And so we take the total charge of the disk and we divide through by the area of the disk, and that is equal to my rho sub s. So, so this is the result that we get. E sub z, as the disk becomes very large, turns into a rho sub s, a charge per unit area on the disk, over 2 epsilon naught. So this result is really interesting. This is a field at z is equal to h due to an infinite plate of charge. Notice that E sub z is independent of the observation point, h, or z, or where the disk is. But I actually meant to put h here. All right? So no matter how far away you are from the plate, the field you experience at the observation point is the same strength, as long as the radius of the disk r is much, much larger than h. Thus, the field does not decrease as the observation point is further from the now infinite plate. So, let's step back. A point charge, we had the field decrease according to 1 over r squared. So the further you went away, the strength of the field decreased according to 1 over r squared. So quite quickly. When we had an infinite line charge, that decrease was not quite as rapid. It decreased only according to 1 over r, not 1 over r squared. So we lost a r in the denominator, going from the point charge to the line charge. Now going to the plate, we lose yet another factor of r in the denominator, and that takes it from 1 over r to 1 over 1. And so meaning that the field does not decrease at all as we go further and further away from the plate. So quite interesting. And you can think about why this would be and justify it. And in fact, I may have that as a homework problem for you to explain in words the mathematical results. And there is a right answer to that. You can explain this, explain that result in words. Why that would be. All right. I'll leave it to you to develop that a little bit better. Even the statement of the question a little bit better. Okay, let's progress on to the sphere of charge. So now we're going to be stacking up these disks and making a sphere. So now let us do the last integral over the z variable. In effect, stacking disks of various radii to create a sphere. All right, so each disk will have a radius r, but we know from our equation of the sphere that r squared plus z squared is equal to r squared, capital R squared, the radius of the sphere. Thus, r squared is equal, lowercase r squared is equal to capital R squared minus z squared. Again, we're going to want the charge of the sphere. We can go through and do the integral over the volume of the sphere, but we know what the result is right away. The charge of the sphere is simply going to be the charge density, rho sub v, times the volume of the sphere, which we all know is 4/3 pi r cubed. But if you were to go through the integral, you would get that result as well, of course. So that is the charge of the sphere. We sort of tuck that away, and we're going to use that later on. Now for the integral. Fine. We take the result from each disk of radius lowercase r, and we put it into, and we do this next integral, namely the integral over z, going from minus capital R to plus capital R. So this is what we have, and we have, so this can be broken into two terms involving the 1 right here of the within the bracket. That turns out to be a really easy integral to do. Simply rho v capital R over epsilon naught. And then we have the second integral that's a little bit more difficult and takes a little bit, a few more steps. So we define that as I, this integral, and we attack that integral right here. All right. Note that we don't include within I this negative. So it's just this right here. The rho v over 2 epsilon naught. Going from here to here, we put in what my r, lowercase r is in terms of capital R and z. Remember from the prior page, we had lowercase r is squared is equal to capital R squared minus z squared. So we put that in, and that's what we get right here. And so this is now I, and so we're going to let this r squared plus h squared equal to d, just d. So this is what we have here. We do our first substitution of letting 2hz equal to u. So we find what du is, and we find what our new limits are in this new variable, and this is the integral that we have once we do that substitution. We work with the numerator. We note that we could put this numerator, we can subtract d and add d and group them in this way such that the numerator turns into two terms. One that has just a constant. H and d are both constant. And so we can take that out of one integral. And then this term matches what's in the denominator. And so this integral turns into this one that involves two integrals, but both are quite easy. But both require another substitution, and so we let v is equal to d minus u, and therefore dv is equal to minus du, along with new limits. So both of these integrals change change into this one after we do the substitution. Both are really easy now to do and to put in the limits, and this is where we just have to be a little bit careful because my observation point is always going to be outside the sphere. At least that's what we're going to be doing for this problem. Thus, h is always greater than r. All right? So when you do this integral, it's quite easy to mess up the signs of the integral because you're working with a minus h, but you're squaring it, where h is going to be greater than r, but you're going to so you'll get a negative number in there, but you square it, which makes it always positive. But then you're going to be getting the cubed root here and the square root coming out of this one, and so you have a chance of messing up the signs because you might carelessly or erroneously or mistakenly get back the negative sign that's within this right here. And so you just have to be really careful with that integral. And what you find is that you have to take the absolute value of this. All right? Once you do that, you certainly get the right answer. You just have to do the integral correctly. Once you do that, the I term turns into this. I is equal to this right here. Now remember, E of z was the original, the very simple integral that we did on the first page of this calculation, minus this I term. So we have minus this and minus this, which has a minus in front, so it turns into a plus right there. So this cancels with this, and you're left with this right there for E sub z, where this is the volume charge density. So when you express this in terms of the total charge of the sphere that we calculated on the first page of this calculation, we get this right here. So E sub z is equal to q sphere over 4 pi epsilon naught h squared. Where, remember, h is the distance from the center of the sphere now to the observation point. So we look at this and say, wow, this is the same that we would get from Coulomb's law. But I'm stepping ahead, actually. Let's go down to this page. Because this was right along the z-axis. Our observation point was on the z-axis, and we used symmetry early on to argue that we only had a field in the z direction at that point. So this is for a particular point, meaning on the z-axis. And the question is, can we generalize it to any point, anywhere in space? And the answer is yes, just like we did for the line charge earlier on. In the lecture, we can do it in this case here. Due to the symmetry of the charge configuration, we can generalize this result to any observation point outside the sphere, such that we know that the field is always pointing radially away from this sphere, radial in terms of spherical coordinates now. My h turns into r, where r is simply the distance between the center of the sphere to our observation point. So E vector is equal to q sphere over 4 pi epsilon naught r squared in the r hat direction, is the general solution using the direct integration method. Okay. Finally, we can now state the surprising conclusion, potentially surprising. This is the same result as that of a point charge of infinitely small radius and charge q sphere, the same charge. So therefore, spreading out the charge over a volume of a sphere had no effect on the field so long as my observation point was larger than the sphere. All right? And so you could just be right above the sphere, just very close to the sphere, the surface of the sphere, your observation point. And you would still have the same electric field as if that charge was all compressed down to a point charge at the origin of your coordinate system. So, quite interesting. This result, along with example 1 of the infinite line charge, suggests something quite remarkable. Does the field not care about the particulars of the charge distribution? Does it not care that the charge is uniformly distributed over a sphere and rather than compressed into an infinitely small point charge at the origin of your coordinate system? Or are there differences that can be measured at a particular observation point? And so the answer to this is that under certain conditions, that is entirely true. That speculative statement right there. All right. To uncover the condition, we need to learn more, study more about the second method to calculate electric fields, namely the method that uses Gauss's law. All right, so let's look into this. Gauss's law method. We can solve for the electric fields produced by highly symmetric charge distributions by using Gauss's equation, the very first equation within the celebrated Maxwell's equations, the set of 4 equations that describe everything about electromagnetics to a certain degree. And so that was del dot E is equal to rho over epsilon naught. All right, quite a short formula, but very powerful. So we're going to work with this, and now we're going to integrate both sides over some volume, any volume that we choose. All right, any volume that we choose. And we integrate both sides. So really, we should have volume. There. All right. So this side here is very simple. The epsilon naught is a constant. So this side here is simple. The epsilon naught is a constant. We can take it out in front. And then we just simply have the integral over volume of rho, which is simply the total charge enclosed in our volume. All right. So the right-hand side of this equation is very easy to perform, is to calculate. The left-hand side is the one we're going to work with, and the one that's going to impose the special conditions. So we first use the divergence theorem to change this volume integral over to a surface integral, where we're going to integrate over the surface that encloses this volume. All right? And again, whatever volume we choose. We draw an imaginary boundary around this volume that we're interested in, and that boundary, that surface, is called the Gaussian surface, G sub S, Gaussian surface. And my Q enclosed is the charge within this Gaussian surface, within the volume of interest. So, where Q enclosed is the total charge within the Gaussian surface, which we abbreviate as G dot S dot. And this is bounding the volume. So we have the volume, we have a Q enclosed, and we have the bounding surface, which is our Gaussian surface. Okay. So we would like to use this equation to solve for E. In general, this is difficult, but for particular charge configurations, it is easy. So we can do so quite easily if the charge configuration has symmetries or invariants of some sort. So let us consider the 2 prior examples, namely the infinite line charge and the infinite sphere. So the infinite line charge, we're going to solve again, but now using Gauss's law method. So we have this infinite line of linear charge density rho sub L, and we're going to apply the Gaussian law method to solve for the field at any observation point outside the wire. So I like to teach students that to do a step-by-step approach when using this method. You first identify the symmetries. Okay. Then once you know the symmetries, you're going to choose a coordinate system based on what you learned from step 1, the symmetries. After drawing the coordinate system, after choosing the coordinate system, you're going to draw your volume of interest that the surface of that volume is your Gaussian surface. And then finally, you're going to solve this integral right here. this integral. I don't know if my pointer shows up. And so you're going to solve that integral, namely solve the problem. So we're going to look for symmetries. Obviously, we have cylindrical symmetry, so we're going to use cylindrical coordinate systems. If we have spherical symmetry, we're going to use spherical coordinate systems. And if we have symmetries that correspond to near symmetries or a pi/2 rotational invariance of this structure, we're going to use Cartesian coordinates. But for this infinite line charge, we have cylindrical symmetry, and so we're going to use cylindrical coordinates, and next step is we draw our Gaussian surface, our volume of interest. And so we just arbitrarily choose a cylinder of any radius r, and a height L. All right, and so our volume is a cylinder of radius r and height L. And the surface of this volume defines our Gaussian surface over which we're going to integrate, period. So, but we use our arguments of symmetry, our symmetry, to our advantage. So, due to the symmetry of the charge configuration, we expect E to only have an r hat component, meaning pointing straight away from the wire. So, E is always pointing straight away from the wire. Okay? Additionally, it is going to have the same strength here as over here, the same strength. Obviously different directions, but same strength there as there, and anywhere around this cylinder, as long as it is the same radial distance away from the wire. All right? So E magnitude on the sides of this Gaussian surface is always the same, the magnitude. Okay. And remember that surfaces, when we're talking about vector calculus, surfaces always are vectors that have a magnitude and also a direction given by its normal vector. All right? And these DS's are always outward pointing vectors, pointing out of the volume of interest. All right? So this integral that we're going to be performing is always E dot ds. All right? So two vectors dotted into each other. And so we look at these three different portions of our Gaussian surface: the top surface, the top surface, the bottom surface, and the side. And we note that for the top surface and the bottom surface, E is perpendicular to ds. E is perpendicular to ds. So E dot ds for those two surfaces are always 0. Whereas E and ds for the side are always parallel. So E dot ds for the top and the bottom are 0, but for the side, E is parallel to ds. And remember, E, the magnitude of E, is the same anywhere on the side, as long as we're working with the cylinder of a constant radius. So we can take E outside the integral, and we simply have this, where the integral turns into just the area of that surface, which is the circumference times the height, 2 pi r times the L. And Q enclosed is just simply the linear charge density times the length of the line. So it's rho sub L times L. And therefore, we can go directly to the result of E 2 pi r L is equal to rho LL over epsilon naught, and divide through by 2 pi r L. The L's cancel, and we're left with, and we employ symmetry to say this electric field has not only this strength, but also oriented away from the wire, radially away from the wire. And so we now can go directly to the answer as E vector is equal to rho L, rho sub L, over 2 pi epsilon naught R hat. So we compare the length of the calculation using Gauss's method as compared to the length of the calculation using the direct integration method, and find that it was far easier to solve for the electric field using the Gaussian law method than the direct integration method. This was only possible because we had the high degree of symmetry of the charge configuration, namely the cylindrical symmetry. All right, let's see what benefits we can get in terms of efficiency of calculation if we use the Gauss's law method when solving for the uniformly charged sphere. Again, we look to see what symmetry we have. And we have a high degree of symmetry, namely spherical symmetry. Thus, we suspect that we can use Gauss's law to find the field. And that is a correct assumption or suspicion. Due to symmetry of the charge configuration, we expect E to only have a spherical radial, so a capital R hat component. Thus, E is equal to E sub R, R hat. Also, ds is also always oriented in the r hat direction. All right. So that's what we have for ds on our Gaussian surface, as well as the electric field on our Gaussian surface. All right. Now, this is a Gaussian surface. It doesn't have to be the boundary of the sphere. It is at any observation point a distance lowercase r away from the origin. Okay, so the left-hand side of the equation, the E dot ds integrated over the Gaussian surface, E is parallel to ds, so the dot product turns into a product of the two magnitudes. E is constant over the Gaussian surface. We can pull it out to the integral sign. Then we have an integral just over the surface area of the sphere, which is 4 pi r squared. The total charge enclosed by the Gaussian surface is simply rho v times the volume of the sphere, 4/3 pi r cubed, which is q of the sphere. Now, so this r and this r are different. This r is the radius of the sphere. This r is the distance from the origin to our observation point, which is on the surface of the Gaussian surface, which is on the Gaussian surface. All right, and so my charge configuration will be right here, say, and this distance there is r, and my observation point is at any distance of interest at some position r, and this is my Gaussian surface. All right, so therefore we have magnitude E times 4 pi r squared is equal to q sphere over epsilon naught. We use our symmetry, and we divide through by 4 pi r squared, use our symmetry to say that the electric field anywhere in space is equal to q sphere over 4 pi epsilon naught r squared in the r hat direction, which is what we obtained with the far more difficult direct integration method. So we got this result within a page, where the direct integration method took a lot more than one page. And so for these highly symmetric structures, in this case spherical symmetry, and in the case of the line charge cylindrical symmetry, we could use the Gaussian law method and be able to calculate the fields in a much more efficient manner. Okay, so that's those are two methods to calculate the electric fields. So we'll be going over this in class today, but being able to save some time because we have this video that explains all the details, and then we can use some of the time in class to do examples. All right, take care.